robust model of the power duration relationship, or as most people know it, the mean maximal power curve. That then led to some questions about, well, does this mean that, what we're currently familiar with is going to go away, and what are the implications with respect to normalized power, etc. If you look at that slide, you notice it doesn't say anything about normalized power. It doesn't say anything about the performance manager chart. It doesn't say anything about TSS. And while there's a desire to work the way toward modeling adaptation instead of stress, which would lead to a new relationship, a new model of the relationship between training and adaptation. We aren't there yet. Those items in bold are things that we've implemented in 4.0. The things that are not in bold are things that we're thinking about and may or may not see the light of day, depending on whether or not they pass muster with me. But just to reassure the folks who are wondering about, well, what happens to my beloved performance manager chart, not only is it still in WKO 4, it's actually been promoted to the opening or the home page here. So you can see it on the lower panel, the details pane there. So you have the ability in the top pane to select the athlete that you're coaching, and you could click through them one by one by one by one and see the performance manager charts right up front. So get the 64,000-foot view of the forest that constitutes their training. So no, it's not going away. If anything, it's more prominent now than it ever was. So hopefully that gives people a little bit of reassurance. We then moved on from talking about the Parthenon to how you actually evaluate mathematical models. And my #1 take-home point there that I wanted people to remember is that for a nonlinear model, the R-squared really doesn't tell you anything. You need to look beyond that, and there are a variety of different tools that can be used to assess the robustness of mathematical models. Again, recalling that models aren't right or wrong, it's more an issue of what is their domain of validity. Are they pretty narrow, pretty constrained, only work in certain situations, or are they very robust and can only be broken at the extreme edge cases? And again, it's looking at the residuals is really the workhorse here. I then took that background and we looked at half a dozen different equations here. I won't say half a dozen models because Pinot and Grappe isn't really a model. It's a mathematical smoothing function, but it doesn't really have any physiological underpinnings in its structure or anything like that. Well, I looked at a half a dozen different equations that you can find out there in the scientific literature and presented on those. In fact, I evaluated over a dozen different models or permutations of different models to try and find one that would serve as the foundation for this Parthenon. And as we talked about, and you can see from these examples here, none of them fit the entire power duration relationship. As well as is necessary for me to achieve my goals and the things that I want to accomplish. By the way, in case anybody's confused by this, this is just a representative rider with their actual mean maximal power duration relationship from an entire season here that I've shown. So it just gives you a feel for the curve fits. In fact, I tested these models, as I said, during week 1 against a very large selection of such data. And then, relying on the tools that I discussed in terms of how you evaluate mathematical models, we looked at the normalized residuals from these representative models out there in the literature as a function of the duration of exercise, the duration of effort. And again, what you find is some of them work okay, or as, like I said, somebody put it, they work for a while, but then they tend to fail and often fail spectacularly once you move outside of a certain range of durations. The classic critical power model in particular, but also the AIS model, the model of Ward-Smith, well, actually the classic critical power model and the model AIS model, which is a permutation thereof, actually predicts that you can produce infinitely high power at infinitely short durations, and it also predicts that your power should come down to an absolute plateau, which means as the duration gets longer and longer and longer and your power gets lower and lower and lower, then the error, the residual, grows ever larger from that point. And so you have modifications too, for example, the critical power model, such as Morton's 3-parameter model, which attempt to address that, that question. We also talked about Ward-Smith's equations, which approach the notion of you have a balance of aerobic and anaerobic energy production differently, rather than postulating that it can be modeled as if you have a finite capacity. They modeled both aerobic and anaerobic energy production as time-dependent processes. And then again, finally, the Pinot and Grappe is tossed in there as an example of not only the failings of the scientific review process, but also the idea like, well, what if you punted and just started hunting around for a simple mathematical smoothing function? And then we also looked at external validity, which is the ultimate test of any mathematical model. How well does it predict what you want it to predict? And I illustrated how none of these models really do that great a job of hitting at somebody's truly sustainable power output, although they come out okay in some cases. In particular, if you base your critical power 2-parameter model over longer durations, you can get a reasonable estimate of somebody's true steady state power. Although again, it fails at short durations and it fails at long durations. And again, Pinot and Grappe, since an attempt to predict steady state power is not really part of it, it's just not really applicable here. So the conclusion I reached after going through all of this literature and like I said, looking at a lot of different models and testing them against a very large database of actual data from riders out in the field, talking about tonight. So part 3, introduction of a superior approach, and what I have. The idea then, here's the model fitted solid line to that same representative set of data I've shown for everything else, where power is modeled, power at any time t is modeled as being a function of 3 physiological traits or characteristics that provide a unique description of somebody's power duration relationship. That is their maximal power, or Pmax, their functional reserve capacity, or FRC, their functional threshold power, and maybe one or more other parameters. Now, if you've been hanging in here thinking or hoping that I would actually be showing you the equation, I'm afraid I'm going to have to disappoint you, because if I did so, by morning you would see it instituted in Golden Cheater, Sports Tracks, Strava, and all the other programs that have popped up in the wake of what was TrainingPeaks and what is now WKO+. So it's going to have to remain a secret, at least for now. To give but an example of that, I put this slide as a teaser onto the Training and Racing with a Power Meter Facebook page, and it took all of 7 minutes before people started posting questions and started trying to tease out, well, what was the structure of the model, how many of their parameters, etc. So while I can't show you the actual model equation, what I can do is I can show you how it works, and so that's what we're going to be talking about for the rest of tonight. Again, though, first definition of terms, just to make sure we're all on the same page here with respect to these acronyms, etc. In these, in the case of FRC, a new term. Pmax is the maximal power that can be generated for a short period of time. very short, although it would entail at least one complete pedal stroke. In essence, it's the y-intercept of the model fit, which is going to be the highest values you're going to see are going to be dictated by how frequently your power meter can measure power. And since all of them right now report power at a minimum for one complete pedal revolution, and usually, in some cases, longer, like 1 second, etc., it wouldn't be any shorter than that. The units here would either be in watts, or if you want to normalize it to body mass, watts per kilogram. Functional threshold power down at the bottom is one you're already familiar with. It can be defined, has been defined as the highest power that can be sustained in a quasi-steady state for a prolonged period of time. I made the point early on, you notice that there's no 60 minutes on here. There's not even a squiggle 60 minutes on here. While you can use 40K TT power as a surrogate estimate of functional threshold power, it's not the absolute definition. Of course, the reason you can use something like 40K power is because the power duration relationship is so flat out at that point that it doesn't really matter much or significantly whether you use 1 hour, squiggle 1 hour, 40K, 38K, what have you. Again, units could be watts or watts per kilogram. The new term, the one you're going to have to add to your vocabulary, is functional reserve capacity. And since it's quantified in terms of work, then the units would be, if you're dealing with cycling data or power meter data, the units would be kilojoules or joules per kilogram. Now, if you're at all familiar with the scientific literature or with the notion of critical power and the monad model, you're probably saying to yourself, but wait a minute, that sounds just like W prime or anaerobic work capacity or whatever the nom de jour is that people want to use nowadays. And you're right. In terms of the words used to define it and the concept, it is essentially the same thing. Mathematically, however, I'm calculating it differently. And as I'll show you later, functional reserve capacity doesn't correlate very well with W prime. And so you can't really use the same term to describe them because they aren't exactly the same thing. I also wanted to avoid a bit of the maybe baggage, you might say, associated with the established having to be dispelled now as people move back away from that term AWC. So starting afresh, just like I did with functional threshold power, decided to call it functional reserve capacity. And at this point, I've been asked to present this slide to make the point that registered trademarks are being pursued for these following terms, and unauthorized use is expressly prohibited. I feel like I should be the announcer at the NFL games. This broadcast is the property of NFL or whatever. All right, so now that you're all on notice, let's return to actually talking about what's fun to talk about, and that is the model and how well it functions. Like I said, I can't show you the equations, but I can show you how well it functions. And again, if you recall in week 1, I talked about various tools you can use to evaluate how well a model fits data. So starting with just looking at the distribution of the normalized residuals here. Again, in the ideal situation, your model would not be biased. It would be missing on the high side of the actual data points as often as it misses on the low side of the actual data points, and that it wouldn't miss by a large amount very often. If those ideals are achieved or at least approached, then the normalized residuals should have a normal distribution. And as you can see here, it may not be a perfectly normal distribution, but it's very close to one. Unlike the other models where you have this huge heap of cases where the model grossly overestimates the power output that somebody can make at either short durations or long durations. The model in WKO4 doesn't have that bias. Similarly, and I've put various versions of this slide out there many times over, if you look at the normalized residuals as a function of duration, there isn't any inherent bias at any particular duration. That is, the normalized residuals here, plus or minus 1 standard deviation, overlap 0 all the way across the board. And it's only when you get out, like I said, we have close to 100 athlete seasons here included in this data set. It's only when you get out here that the number of individuals start dropping off, because only a few people do really long rides and one person does a really long ride, that you see the standard deviations start to increase, etc. So it does a good job of fitting the data all the way from 1 second out to, well, 20,000 seconds or thereabouts. As what I was striving to achieve in order to provide a solid foundation for this Parthenon of new ideas. Another way you can evaluate models, or another important aspect, is to make sure that the model is not over-parameterized, which you can assess in part by looking at a correlation matrix of the various parameter estimates that go into the model equations. If they are significantly correlated with each other, there's a possibility that you've over-parameterized the model and you're representing what is really one thing as if it were more than one thing. And as was the case with the other models that we looked at, this is not the entire correlation matrix, but to show you the correlation between the primary parameters, there is a statistically significant correlation between Pmax and FRC and between Pmax and FTP, but no relationship between FRC and FTP. So that suggests it's possible the model might be over-parameterized. On the other hand, we're dealing with very large data sets here, and not all that many parameters, so it's not that likely of an explanation. Instead, I think what this reflects is the fact that I'm dealing with data in raw watts, and therefore, bigger people have higher maximal powers, they have higher functional reserve capacities, they have higher FTP values. They're just better and more powerful across the board compared to smaller and or lesser accomplished cyclists. And in fact, that interpretation is consistent when you actually look at the CVs of the model fit parameters. Remember, we're doing an iterative approach to curve fitting the data here, which means in addition to coming up with an estimate of the parameter, you also obtain an estimate of the uncertainty associated with that. So when you fit the data fit the model to the data, you have a standard deviation of your parameter estimate, which if you divide it can be expressed as a coefficient of variation. If a model is over-parameterized, that is, if you're using more than one thing to represent what is really just one thing, then your CVs of your model fit parameters tend to be very large, because it only takes a tiny little change in one to compensate for a change in the other. And when the iterative curve fitting procedure is trying to find the combination of numbers that best explains the experimental data, it turns out that there's a large number of combinations that do almost equally as good a job of explaining the results. On the other hand, as you can see here, the CVs of the model fit parameters are actually quite tight, with FTP in particular only 1.2%. So that supports the conclusion really that Pmax, FRC, and FTP are different things. They are unique signatures of somebody's power duration relationship, or if you want to think of it, the shape of their mean maximal power curve. And by the way, it isn't uncommon when doing this kind of modeling to see coefficient of variations of your model fit parameters of 10 to 20%. even with a really good model. And then occasionally when you have things that are either over-parameterized or particularly noisy data, you might be dealing with coefficient of variations of 100% or 200%. So to pull off CVs of this narrow a band is actually quite nice. And by the way, I've made the point repeatedly in earlier presentations as well as in posts to various fora that, unless you provide the coefficient of variation around your parameter fits, you're not really telling people the whole story. You're claiming that you can nail something down to, an absolute value, an absolute science, but if all you give them is the R-squared, they're left with this great impression. Wow, look, he's got an R-squared of 0.98. It must work really well. When in fact the parameter estimates aren't all that stable. And actually, this is the case of the impulse response model of Bannister. There's a paper, Hellard, where they used Monte Carlo simulations and repeated sampling of the data, et cetera, to look at the stability of the parameter estimates as well as and see the extent to which it's over-parameterized. So, well, it wouldn't be fair to talk the talk if you weren't willing to walk the walk. So here again, a screenshot from the beta of WKO4, and yep, right there on the home page under power duration metrics, you can see we not only give the values for Pmax, FRC, and FTP, but we also give the standard deviation of the parameter estimates. So you'll always be able to know whether you've got a good fit and you've got a good estimate based on the model, or whether maybe your data are noisy, or maybe the modeling process got lost in the weeds. It fell into a local minima when it was trying to minimize the sums of squares. But you'll always have a feedback in the program as to how much faith to put into these model fit parameters. And then again, you can also show, here's the curve fit for this athlete who's highlighted here in the bright white against standards that we'll be talking about next week. So if you were coaching a bunch of athletes and you kind of want to see how they compare, you could just click on this athlete. Whoops, I jumped ahead. Oh, that was us at Elephant Rock State Park last weekend. You could, so you could just scroll right through them right there. And you can immediately see where somebody's strengths and weaknesses fall. This person is pretty much middle of the road in terms of their sprint power, and they're pretty much middle of the road out here at longer durations, but they're stronger right here in the midpoint. Another way of validating models, again, is to look at external validation. And here, for a subset of all of the subjects who had done a longish TT, a comparison of their model-derived FTP against their average power during that time trial. The slope and intercept here are not significantly different from 0 and 1, respectively, which is, the intercept and slope are not significantly different from 0 and 1, respectively, which is what you want, right? You want your regression line to fall right on the line of identity, ideally. And the standard error of the estimate is plus or minus 0.8 watts or plus or minus 0.2%. So yeah, feed me your power duration data prior to going out and doing a TT, and I can crunch it through the model, and provided you haven't been sandbagging in your training, I should be able to predict your TT power to within that degree of precision most of the time. Plus or minus 1 standard deviation is plus or minus 0.2% here. And finally, although the estimate of Pmax is not it doesn't represent actionable intelligence to quite the same extent as the other parameters of the model do, in that you could always look at somebody's short duration power without any model and know whether they're a good sprinter or not. Nonetheless, there are occasions in which it's useful to have a best fit curve fit estimate of that sprint power. For example, to identify outliers, cases where the person's power meter went, haywire for 1 second or 2 seconds or 3 seconds or something like that, and inflated their short-term power. So here, for the entire data set, I've compared the model predicted, or the model-derived Pmax against the actual measured 1 second power. And you can see there's a nice close correlation between the two. Because it's a linear curve fit, in this case we can rely on the R-squared value as an indication of the tightness of the fit there. And the slope is not different from 1, and the intercept is not different from 0. So yeah, the model also works in terms of predicting sprint power, although again, that's not all that surprising really. Still, it's another way of testing how well does this model work. All right, so we've talked about and again, I made the statement, the saying down in Texas, it ain't bragging if you can back it up. Well, let's see whether I can back it up. Let me start by just reminding you what these residual curves look like. Things like critical power based on 1 to 10 minute efforts, or critical power 3 to 30 minute efforts. They work for a while, but then the residuals increase dramatically thereafter, and in fact would eventually go to infinity. 3-parameter model bends that initial part down and tries to hit the Pmax. So you can see it does a better job at shorter durations, though it still has that funny hump in there. AIS model seems to be, it's kind of okay on average, but it is swooping above and below and doesn't spend very much time at all close to 0. The Ward-Smith model is similar to the 3-parameter model in terms of the residuals, but neither one does a very good job of fitting the curve out at later durations. And Pinot-Garape's just using a mathematical smoothing function, you can see it's biased, and the residuals start high, go low, then they go high, then they go low again, and it looks like they're coming up again as well. Whereas I showed you previously, the normalized residuals plotted against duration for the WKO4 model show no such bias. They overlap 0 across the entire range of durations. What is that, 5 orders of magnitude of durations? Yeah. And they are very tight, less than 5% pretty much across the board. Another way of summing up all of that data is to calculate the root mean squared errors, and that is take the residuals, square them, sum them up, divide by the degrees of freedom, and then take the square root, so you're back to the same units as you had initially, as a way of comparing different models and how well they fit the data. And the advantage of this as a calculation is it gives us an estimate of theta, so theta hat, which is equal to the square root of the variance, in other words, the standard deviation, or in the case here, we're predicting something, and really the standard error of the estimate, plus the bias. If you had a perfect model, then the variance would be 0 and the bias would be 0, and your root mean squared error would be 0. So the closer to 0 you get, the better off you are. Now, because this is theta hat, that isn't, it's a sample-based estimate of the population parameter theta, it is dependent upon the sample that you're using to do the calculation with, but I use the same sample for all of these comparisons, obviously. But that's why the values you see here for the root mean squared error do not go to infinity, when in fact they should, for these models that predict that at infinitely short time you'll be able to achieve infinitely short power. I'm not feeding infinitely short data into the calculation. The shortest duration was 1 second, and therefore you don't go all the way to infinity. Nonetheless, you can see that all of the values shown in bolded red there are significantly greater than the 0.3 plus or minus 0.1% for the WKO4 model. And again, the ideal is that the closer to 0 you get, the better off you are. what's also clear if you look at this, the classic critical power model, again, because it overestimates at short and long durations, has a very high root mean squared error. Kicking the can down the road and using longer durations gives us a better estimate of your true steady state power, but it actually causes you to mispredict to a greater degree at shorter durations. And so the overall root mean squared error when you're trying to model the entire power duration relationship actually goes up. And then you can see how forcing the curve to bend over like the three parameter model does, or the Ward-Smith model does, knocks down the overall root mean squared error quite a bit just by being able to fit part of the curve, more of the curve better. Although again, when you look at the distribution of the normalized residuals, it's clear these models, especially the Ward-Smith model, are biased at longer durations. Conversely, you can see Pinot and Grappe's approach. It fits okay at long durations. And so despite the fact that you have that funny S-shaped wave, the overall root mean square error is better than you have with the critical power models. So if you're trying to describe the overall curve, this is actually a better approach, even though it has all kinds of biases, et cetera, in it. Nonetheless, the champ is the new model. Moving on to trying to look at how these things compare in terms of external validation, how well they do at predicting FTP, and that is a power that you can maintain in a quasi-steady state for a prolonged period of time. As I pointed out in the first week, the critical power model, 1 to 10 minute, tends to overestimate FTP. So the slope ends up being less than 1, the way I've set up my X and Y. So it's statistically different from 1.0. And your standard error, your coefficient of variation is 1.5%. And again, you have a bias because it's significantly different. I made the suggestion, way back in 2003 or something, that we go back to the early convention in the scientific literature of using longer durations that people used to use, and that actually brings your CV down for predicting FTP, but your slope is still different from 1. The 3-parameter model, both the slope and the intercept of the critical power versus FTP are significantly different from 1, so that's less than ideal. The AIS model, as I showed, on average, gets it right, in that neither the slope nor the intercept are different from 1 and 0 respectively, but there's a huge amount of scatter in the data so that you're predicting FTP to plus or minus 20.5 watts, or 6.8%. The Ward-Smith model is also biased. Pinot and Grappe, your maximal steady state power is not a model parameter included in it, so it's not applicable. And only the WKO4 model achieves the ideal goal of having a slope not different from 1, an intercept not different from 0, and a coefficient of variation of predicting FTP of 0.5%. Another way of sort of looking at the same data, the same ideas here, is to actually look at the parameter estimates themselves for these different models. So Pmax, W prime or FRC, and critical power or FTP. The values shown in bolded red are significantly different from that of the WKO4 model. So the critical power model, 3-parameter, gives you a higher estimate of your Pmax. The Pinot and Grappe's model also gives a much higher estimate, and only the Ward-Smith model gives a value that's comparable to the WKO4 model. In terms of W prime or FRC, the critical power 1 to 10 gives you a significantly smaller value for W prime than FRC from WKO4. If you push the time out to 3 to 30 minutes, that brings down your estimate of critical power, but it means that you're increasing the W prime value, and as a result, you end up with a number that's not significantly different from the WKO4 model. But if you then try and make the curve bend over, you end up with an even greater value here. So it's significantly different from the 4.0 model. The AIS, on the other hand, model gives you a significantly smaller estimate. So in terms of, one of these things is not like the others sort of stuff. The Ward-Smith model is similar in terms of Pmax, but you can't really say how they compare in terms of W prime, because that's not part of the Ward-Smith's model. CP based on 3 to 30 minutes worth of data inclusive gives a similar estimate for your reserves, but you can't really say how they compare in terms of Pmax because it doesn't estimate your Pmax value. And finally, when you look at the critical power values, using CP 1 to 10 gives a significantly higher value than the new model. This, in fact, is why I made the suggestion way back when that people use longer durations. And in fact, if you do, you get an estimate that is, on average, nearly identical to that of the 4.0 model. The 3-parameter model gives even lower values still, to the point that it's significantly lower than this. The AIS model is also significantly lower and comparable to the 3-parameter model. And the Ward-Smith model, on the other hand, really overestimates what you can do. In fact, I made the point when I was talking about that one, you end up with estimates of critical power that are actually above power at VO2 max. And of course, some of this is not really news. It's already been shown in the scientific literature that using longer durations in the calculation of critical power using the classic 2-parameter model results in lower estimates for critical power, higher estimates for W prime. And similarly, it's already known that the 3-parameter gives you lower numbers still. So there's nothing really new in that context. What's new is comparing it to the WKO4 model. Now, when it comes down to which of these is actually, telling you the truth, I keep talking about a quasi-steady state, a steady state in terms of exercise metabolism. Originally, it was believed that the critical power model would give you an estimate of maximal steady state. That is based not only on lactate values, but also pH, on ventilation, and on oxygen consumption, and hence would demarcate the division between heavy exercise that can be maintained in a steady state and a quasi-steady state, or severe exercise consumption drifts inexorably upwards towards, if not all the way to, VO2 max, and fatigue occurs much sooner. But in fact, when people started looking at that, what they found was that if you use shorter duration efforts to calculate critical power, you end up overestimating somebody's true maximal steady state exercise intensity. So here's a paper from 1992, McClellan and Chung. They used laboratory-based tests of 2 to 15 minutes in duration, and then ask people to either exercise, to pedal continuously at an exercise intensity corresponding to their critical power. We can ignore individual anaerobic threshold here. This is based on blood lactate measurements. But you can see how that if they use a 2 to 15 minute time range to define critical power and then ask people to exercise at that power output, it's supposed to represent a steady state exercise intensity, but in fact it doesn't. VO2 drifts upward, ventilation drifts upward, and people fatigue after only 15 minutes of exercise. And therefore the conclusion here is that using this approach overestimates the metabolic rate associated with a steady state. Similarly, if you don't want to look at lactate values, people then started focusing more on the notion of oxygen consumption and the slow component of VO2. Primarily, all of this is coming off of a paper from 1998 by David Poole, in which he concluded or demonstrated that, at least in that one study, critical power, even though it was based on short duration tests, did represent a steady state exercise intensity, and that if you want only 5% above it, you saw a drift in oxygen consumption. But in fact, in these follow-up studies, as you can see, nobody can reproduce that observation. So here, using tests of 1 to 10 minutes in duration and then asking people to exercise at their critical power, oxygen consumption drifting upwards, obvious slow component here, no leveling off in VO2, i.e. we do not have a true metabolic steady state being achieved here. And so these authors also conclude critical power based on 1 to 10 minutes does not represent a sustainable steady state intensity of exercise. And then finally, I'm going to beat a dead horse here. Yet another example, this one from Pringle and Jones, where they were looking at critical power-based tests 2 to 15 minutes in duration, and they end up demonstrating if they have people exercising at critical power, their oxygen consumption drifts up significantly over time. Whereas if they have them exercising at their maximal lactate steady state, then their oxygen consumption remains constant over time. And the same is true with respect to changes in ventilation and lactate. So their conclusion was that it was really the power at maximal lactate steady state and not the not critical power based on tests of 2 to 15 minutes in duration that really represents the upper limit of the heavy exercise domain and the beginning of the severe exercise intensity domain. Now, again, this is not news. Van der Waal, in a review of some of their work as well as the rest of the literature, concluded, and I'll quote from the abstract here since there weren't any nice graphs in the picture and I can't present you the whole text. Experimental data collected during local knee extension and general running and cycling exercises suggest that critical power could correspond to a steady state, provided that critical power is calculated from heavy submaximal exercises only, ranging between 6 and 30 minutes. When critical power is calculated from short supramaximal exercises, this power output is higher than the power output which corresponds to a lactate steady state or an oxygen uptake steady state, and does not correspond to a power output which can be sustained for a long time. So that's the state of the literature as of 2002, and it would take a very selective reading of the scientific literature to reach any conclusion otherwise, which is why I find it very puzzling that then Andrew Jones goes on to write review articles, ignoring his own previous work here, and tries to make the argument that critical power determined using tests of 2 to 15 minutes duration is really the magic marker that we're looking for here. Of course, the good news is if you're a cyclist and interested in winning bike races, you don't have to worry about these kinds of complications, and you can be very more pragmatic and just think again about, well, the heck with what's going on physiologically. Let's just think about the numbers that we're collecting with our power meter out in the field and see if we can leverage those to better prepare for competition and spend more time on the top step of the podium. So returning to this slide and just thinking about the parameter estimates, another question you might have then is like, okay, well, they give me different results. Which one's right? Just to further illustrate the differences between the different models, I put this up as a teaser slide as well, and I quoted Shakespeare. What's in a name? That which we call a rose by any other name would smell as sweet, or maybe not. As you can see, even though, I should back up here. CP 1 to 10 gives us a smaller value. CP 3 to 30 gives us a similar value as the WKO4 model. The 3-parameter model gives a higher value. The AIS model gives a lower value. But even in the cases where they give similar values, they're not all that similar on an individual basis. These are the regression lines for the various models. The AIS model down here, the 1 to 10 minute here, the 3 to 30 minute data here, And finally, the critical power 3-parameter model, W prime measured using those various approaches, plotted against functional reserve capacity, calculated using the new model for the same individuals. And you can see that not only are the slopes generally different from one, with the exception of the 3-parameter model, but the correlations aren't all that high, even in the case of the 3-parameter model. So not only do they give different numbers on average, even when they give the same number on average, that is the 3-parameter model, they give different numbers for any given individual. And this is why I decided I can't call it W prime. It's calculated differently, and it seems to be measuring something else, even though conceptually it is the same thing. Now, then you want to say, well, which is the real reserve capacity? Which is the truth? Well, then we have to go back and think about this. At the end of the day, remember what I said about mathematical models. Mathematical models are theoretical constructs that may or may not have a basis in reality. Well, I don't think there's any question that these various models have a basis in reality, and that is they are attempting to measure physiological functions. And you can do a lot of experimental interventions to test those ideas, but the bottom line is that it's still a mathematical calculation. You can't measure W prime itself any other way than to do a series of exercise tests and fit a model. Similarly, you can't measure FRC any other way other than do a mathematical model. It may reflect, physiology, but it's still a mathematical calculation. So which is the real answer? Which is the best answer? Which is closest to the truth? Well, which model best describes the data? I think I've shown you over and over again that the WKO4 model is a better representation of the actual data than these earlier models. So by that argument, I would say that FRC is what we're really going after here. Finally, again, continuing on the theme of external validation, talking about the ability to predict max power, although again it doesn't really represent actionable intelligence to the same extent as some of these other things might. In this case, I've flip-flopped the axes in order to put WKO4 on a regression as well. So in this case, we have the measured data down here and the predicted over here, which is why the regression of x on y is not the same as the regression of y on x, which is why the slope and intercept are different for the WKO4 model than what I showed you previously. But be that as it may, you can see that the Pinot-Ingrape approach grossly overestimates the power that somebody can make for just 1 second. The 3-parameter model comes closer, but still tends to overestimate, and in fact, it does so statistically significantly, as I showed previously. Ward-Smith's approach and the WKO4 model do not overestimate. They're good on average, but you can see there's a much higher correlation, much higher R-squared with the WKO4 model than even the Ward-Smith model. As well as with FTP, the new model also outperforms these other models in its ability to predict somebody's true maximal power. Well, that's the statistician's way of kind of looking at how well does this model work. Another way to test how well a model works is to see whether it's sensitive to interventions. And of course, since I'm not an applied sports scientist, doing formal studies, what my tool here is simply to look at my own data or the data of others and see what happens when they change how they approach their training. So here are the model-derived parameters for myself, yours truly, for 2000 through 2013. I got a power tap in first time. I got one of the first power taps in 1999, but it wasn't downloadable yet, so I don't have power data from download until 2000. From 2000 to 2003, I was training for mass start road races, and in fact, after using the power meter for about a year, recognized that FTP was where it was at, and that especially for a one-trick pony such as myself, so really made that a true focus, and had one of my highest FTPs ever that year, and also had one of my best competitive seasons ever. So FTP, although it's kind of squished out by the axes here, yeah, the peak is at this point. I then in 2004 and 2005, I actually trained for the individual pursuit. So changed the foci of my training to emphasize a lot more level 6 and level 7 to some extent, but a lot of level 6 type work. Painful though it might be to see if I could do anything in the 3 kilometer. And yeah, I'm a time trialist masquerading as a pursuiter, and so can't make the podium at Masters Nationals, but it was fun. It was different. But you can see how when I changed the focus of my training to emphasize improvements in functional reserve capacity, as we're calling it now, the model picks up that big improvement and that big peak. From 2006, 2007, I was basically just riding my bike for fun and fitness while my wife unretired, especially in 2007. And I had no goals, didn't do any structured training, although I was on the bike, like I said, 4 to 6 days per week. FTP, pretty flat, but you can see FRC nosedives back down again. 2008, 2009, I was focusing on time trialing. We went after first the 50 or the 90 plus tandem TT record. John Verheuvel and I took it, and now it's since been broken. And then 2009, I went after the 50 plus record, which was unsuccessful, but just focused all on time trialing. So yeah, did I get my FTP up? I don't know. I'm getting older, right? It's got to be going down over time. But I then took some time off for a little over a year, was only riding about 3 days a week, was lifting weights, was doing some plyometrics and that kind of thing. You can see my FTP tended to drift down, but the big change was a drop in my functional reserve capacity. Then I stopped doing that because I was jumping on the trampoline with the kids in the backyard and developed an ingrown toenail. So I stopped jumping, and then, well, I got to do something, so I started riding a bike again, and that's what I've been doing ever since. And you can see by riding a bike regularly, now I'm probably on the bike 6 or 7 days a week on average. Although again, not a lot of structured training, no races, no particular goals. You can see my functional reserve capacity kind of coming back up again. FTP, on the other hand, pretty flat, and Pmax maybe trending downward as I get older, lose muscle mass, lose strength, power, etc. Here's another case.
Hey, Andy.
Yes.
Andy, I'm sorry, this not to interrupt. There's some oddity in the screen. We can't see when you point at things, so we cannot see your mouse. So now we can. Whatever you just did makes it see.
I have to apologize to everybody. I have 2 monitors, and I'm pointing at the wrong monitor.
Okay, I'm going back to mute.
That's my fault. So, as I was saying, FTP pretty flat, FRC trending down over time, or Pmax trending down over time, and FRC going up when I focus on it, down when I don't, nose diving when I don't really ride a bike much at all, and then coming back when I ride a bike. Here's another case study. I always like to use my wife, because I'm proud of her, but also because she had some dramatic changes and improvements in her performance over the years. So in this case, expressing everything as a percentage of year 1 baseline. So she got a power tap about the same time I did, which was about the same time that she decided to focus on the individual pursuit. And you can see across the years her functional threshold power not really changing much. But as she becomes more and more focused on the pursuit, you can see her functional reserve capacity coming up, and then a huge jump this year, and this is the year she won Elite Nationals in the individual pursuit. And similar with her Pmax coming up. as she focuses on that aspect of her training. If you take that last year, year 4, and then break it off into different periods, knowing what she did during each period, her build phase, if you want to call it that, was the classic hard woman's roadie approach. Lots of 2x20 ergometer workouts on Tuesdays and Thursdays, 4 to 6 hour group rides, quasi races on the weekends with all the Cat 1-2 men, and then enough moderate intensity filler workouts the rest of the time to total out 15 to 20 hours a week for about 4 to 5 months. If you then look at where she was at the end of that build phase and then follow her over the course of the rest of the season, she did mass start road racing from maybe mid-March to when was it, mid-July, around July, no, yeah, around July 1, then got on the track and started to do track-specific training from that point until Nationals, which were in late August, and then about 2 weeks out from Nationals tapered down. So dividing it up in those periods, what you can see is her FTP is the highest when she's focusing on that, as you might expect. It actually tends to drift downward over time. If you don't use it, you lose it, right? What's interesting here is how how it actually drops a little bit even during road racing season, which sort of fits with my long-standing joke about I hate it when the racing gets in the way of my training. Or the fact that people realize nowadays, especially with power meters, that it's very difficult to train productively when you're racing a lot, and so you really have to get fit before the racing begins, and then you ride that fitness as long as you can until you run out of it, and then you have to do a mid-season rebuild or something like that. Or when you're in what Barney King has referred to as race and recover mode during here. Her functional reserve capacity increases when she starts doing mass start races and has to start doing short, hard efforts. But you can see it increases even more so when she gets on the track and starts doing structured level 6 intervals, standing start kilos and standing start 500 meters and that kind of thing. And when she tapers, no real change. And her Pmax, on the other hand, it's here. Doing a bunch of mass start road races doesn't do much for it. You start doing a bunch of track-specific training, including standing starts, etc. It doesn't seem to be improving, but then you have to think of this in the context of our performance manager approach and the realization that there's nothing that's more responsive to freshness than your very short-term power. And sure enough, when she tapers, 20% jump up in her maximal power, presumably was created with all of this track-specific training, but then was also being obscured or hidden by the residual fatigue she was carrying. And it was only when she tapered for a couple of weeks that she was actually able to express that improvement in maximal power. And then finally, if you want to carry the idea to sort of like, well, how low can you go, right? This is I can name that song in one note sort of thing. It's possible to prepare a power duration history chart in WKO4, at least in the beta, looking backward in time to what's happening to these model fit parameters as one day rolls in and another day rolls out. And I'm trying to remember the color coding here. I know this is FTP, so the model derived FTP. I believe purple is Pmax, and then the red would be FRC. So over the course of, it looks like about a 6-week period. Yeah, it's about a month-long period. One day, one workout rolls into the calculation, one workout rolls off the calculation. At some point along here, they did a workout that lifted their power duration curve so that the model says, you've got a new FTP, which has now been, say, sustained. they must have had a big jump in their short duration power, such that the model was now fitting to a higher Pmax, but then they haven't expressed that recently, so it dropped back down, whereas FRC was pretty much constant, if that red line is FRC, until about this same time. They must have had, a really good middle duration effort, lifted the say, in the 30-second to 3-minute portion of the curve up, so that the model-derived FRC goes up. So you can imagine how powerful a tool this can be, or has the potential to be, when you can actually start tracking somebody's changes in somebody's fitness without them necessarily doing any formal testing. Adhering to the idea that, well, training is testing and testing is training, trying to leverage that idea. Excuse me, I'm going to have to cough here. And then finally, if you've got a good model, then it should work for, in multiple situations and not be specific to just cycling. So just for fun's, grins and giggles here, I thought I'd show you what happens if you try and model running performance. Now, these are men's world records, so this really isn't the performance of any one individual. No person could actually do this, since nobody can be both world record holder in the 100-meter and world record holder in the marathon. But nonetheless, if you were going to assume such a superhuman existed, yeah, the model fits there, that data quite nicely, with an average prediction error of only 0.02%. The other thing you can note here is the fact that the one point that falls off the line is the 100-meter record. Well, you also have to realize that there's a considerable acceleration phase that takes place in a 100-meter race. And we're not dealing with power data here, we're actually dealing with speed. So in a way, this speed measurement here, the runner is penalized for the fact that they had to get up to speed, and it underestimates compared to directly measuring their power output. So, of course, far fewer points when you start dealing with, running races and that kind of thing, compared to the power duration data that we collect almost second by second for cyclists. So the model is at great risk of being over-parameterized applied in this context. But nonetheless, it is heartening to know that it does work. You can also apply it to swimming. And so here you see the calculated functional threshold pace and functional reserve distances based on long course freestyle for both men and women. The average prediction error didn't make it onto the screen there for the men, but the average prediction error for the men's data is 0.2%, 0.1% for the women. The other thing to note is, swimmers race over a much shorter span of durations, at least in a pool, compared to cyclists. And I've also tried to apply it to world records in speed skating. And in this case, again, for some reason, I had the average prediction error on there. Doesn't show up. In this case, the average prediction error is about 3%. But again, that's largely due to these early points, which do not make it up to the line, presumably because there's quite a bit of acceleration going on, and of course realizing that speed skaters travel as fast as cyclists do, acceleration is even more important to them than it is to a sprint runner. But yeah, you could model their data, although again you're at risk of being over parameterized. I've looked around, I've tried to find reliable data for dog racing records over vast distances or times. Unfortunately, haven't been able to find any of that. I had the idea that maybe look at horse racing, but again, haven't found any reliable data. I thought, well, maybe I'll look for pigeon racing records, but you can find data for pigeon races over considerable times and distances, but things are, always downwind, tailwind, terribly inflated, so couldn't really rely on that kind of data. But if anybody knows of any reliable data for exercise intensity versus duration for a non-human species, convince you, even though I can't show you the equations, that we have succeeded in developing a robust mathematical model power duration relationship that can then serve as the foundation for all of these other things that we want to do. So with that, I'm going to wrap up. Some things here, and perhaps you've already have some inklings or ideas in your mind that we can then talk about. And I had a list of 10 possible applications in the first week, and also in the, I think I showed that same slide, week 2 as well. So we'll be talking about actual application and getting away from all this, heavy-handed statistics and math. At that point, I want to say thank you for your attention and take any questions.
Great job, Andy. I can tell you the questions were fast and furious today. I think I was able to keep up with most, and I've held a couple of great ones. So I'm going to start with some of my held ones. I appreciate everybody. I tried to let you know I was holding your question. If I missed you, I'm sorry. Question number 1. On the topic of residuals, is there a reason why a bias was not included in the model?
I think this person must be thinking about it in terms of statistics. If you're doing multiple regression, you always have, y is equal to, a times x squared plus, b times x, plus an intercept plus, a big E for the error term. So I think that must be what they're thinking about. So it's not included because the goal is to model the data as best you can. It's really a different, I'm not doing a very good job of explaining here, but it's really just different math entirely. This is not multiple regression. This is not nonlinear iterative curve fitting to a model. The model structure dictates the equations.
Okay, excellent. There was 2 similar questions about the original model that you had there, the original curve fit, that had a little bump around 5,000 seconds, 80 minutes. We got 3 or 4 questions. Can Andy explain the hump around 5,000 seconds duration in the residual graph? Why do you think this is happening? And I've gotten 3 of those very similar.
Yeah, no model is perfect. The other thing here is keep in mind we're modeling actual data from people in the field, and it may very well be that on average people don't choose to ride as hard as they possibly can for more than about an hour and a half, whatever 5,000 seconds works out to be. And so things tend to tail off at that point, and then the model has to do its best to describe what it sees. That brings up the point here is we are modeling actual data here, not normalized power, modeling actual average power over various durations. And so it very much rewards the idea of what have you done for me lately. If you take this model and you apply it to mean maximal power duration relationship from somebody who has been indoors on a trainer and hasn't gone above their FTP for 4 months on end, it's going to really underestimate their Pmax and their FRC, as any of these models would. But that's really a problem with the data set, not with the model. And the solution to that is sort of like, it comes back to, as Jack Daniels has pointed out, when people say, well, they want to, train at faster paces, and his system is based on training paces based on race paces. It's if you want to, train harder, you first have to prove it by racing faster. So by extension of that sort of attitude or perspective is like, do you think your FRC is higher than it is? Do you think your Pmax is higher than it is? You think the model's wrong? Prove it. Bust out an effort, push the curve up, and the model will take that into consideration. Or you can say is, well, I don't need to go this hard at this time of year, and I'm feeding crap data into the model, and therefore I'll discount the model results until I know that I'm not feeding it crap data. But we're always dependent upon the quality of the data that we're feeding into the modeling process.
Great answer, because that sets up this next question, sort of. Is the data set Andrew was using to demonstrate the superiority of his model the same data set on which the model was built?
Again, this is people are thinking about it statistically, like you might do a split halves technique or something like that, or Monte Carlo simulations where you repeatedly draw. Um, the model, the model is full born conceptually. Boom, here's a model. Now take that model, analyze data sets. The result of those calculations was not then used to modify the model. So there's no problem here with any sort of autocorrelation or anything like that. In fact, I made this point in week 1 that when I was comparing the prediction of the various modeling approaches to TT power, I specifically excluded the person's file with their TT performance from their power duration curve so that I wouldn't have a problem of sort of autocorrelation.
Good answer. I'm going to ask this this is 2 questions summed up as one, because I know the answer. And if you don't mind, we've gotten a lot of questions, so there's a bunch I've tackled, but I'm going to ask you to maybe tackle a couple more here. And I can even answer this one, but hold on. Here we go. So Andy mentioned the model function of these 3 parameters plus other parameters. Will he discuss these other parameters? So hold that question. And then, are we going to publish the model? Is it a series of decay terms? So I'll let you tackle those together if you want, or I can tackle them.
We're reporting the parameters of the model that are the most actionable, and I've put all the cards on the table here. I've shown you my evaluation of the model to try and convince you that I ain't bragging. I can back it up. If you don't believe me, you can, in the future, get a trial version of WKO4 and feed your own data into the model and decide for yourself how well it works or how well it doesn't. Other than that, I don't have anything more to say.
Okay, excellent. And everyone, I can tell you, it's difficult. We put out this information, and it seems to very quickly get everywhere and without our permission and controls. And it's not an attempt to do something secretive. It's an attempt to be able to develop the science and control it and know what we're doing as a process and within our control. So it just somewhat is a result of the environment that is today. Here's a great question, a very simple one. Will you be able to identify bad data from an athlete in some type of graphical format driven by the new model?
Yeah, in fact, I gave an example of that in week 1. It jumps out mostly when you're looking at the very short duration. The curve wants to bend over and hit the y-intercept, and all of a sudden you see that their 1 second, their 2 second, and their 3 second values are just unbelievably high. But it also allows you to identify outliers anywhere else along the curve because they're outliers compared to the other data. Now, those outliers could be because there's problems with the power meter and the data collection itself, or it was just a breakout performance. Either way, you've got a nice, smooth function, and you can see where you went above the curve and where you went below the curve. So yeah, as I showed before, and as I'll illustrate again next week, that is one of the benefits of having a robust mathematical model of the entire power duration relationship.
Okay, here's a great one from Alex. How long before the model decides to drop your estimated FTP? In other words, what time period of MMP data is used for the current estimated FTP, FRC, etc.?
Um, what I've been presenting here are athlete seasons, so an entire season's worth of data. As I was showing you in sort of like the how low you can go, it really depends on the context. I've actually gotten what appear to be quite reasonable Pmax, FRC, and FTP data from individuals from a single criterion, so from one file, because the criterion is, long enough and entails enough variation in their effort that you could, at least you're approaching your theoretical maximal power duration curve at various time points. So really the decision to include or exclude data is not a choice of the model, but a choice of the modeler and or the program. I think Alex may actually be asking more about the program.
I think he is actually correct.
Yeah.
What were you showing on the screen? I mean,
you'd have to ask the programmer.
yeah, I think we had selected what he was showing in the summaries was 90-day, was it not, Andy? I think we had set.
I think we agreed it was a 90-day rolling window.
Correct.
Now, whether that's what it remains when we release this onto the wild remains to be determined, I guess. It's one of those things. You can come up with really cool ideas, but it's an enormous amount of work. I mean, an enormous amount of work. I've been basically, all of these presentations have been occupying me full time for the past 3 weeks. So you can imagine if you want to try and analyze, beyond just 100, but if you want to try and get experience with thousands of individuals, it's a huge amount of work, unless you have a program written specifically to do that. And then you write the program specifically to do it, and if you're lucky, things turn out the way you envisioned in your mind and the way your initial test cases implied it would work. And if you're unlucky, it doesn't work out that way, and you wasted time or you have to change it. So it's very much a learning experience here. This is sort of part of the reason why the performance manager approach was secret for 2 years, and we had our secret UTSS list. It was so that we could gain experience with it before turning it loose on people.
Yeah, Andy, if you don't mind, if I can add, because I tackled a ton of these questions. You guys, we plan on releasing a WKO 4.0, a 4.1, and a 4.2 in a very rapid succession. Besides bug fixes or any little things in between, not talking about just upgrading as we go. The reality is some of this Andy has created an excellent science. A lot of people ask me if we or Hunter or the Peaks Coaching or whoever is testing this or training athletes with it. Yes. And we're still learning. And the idea is that there's going to be some evolution. So even when Andy and I said 90 days, we got 1 or 2 questions about, well, can I adjust that? Yes. I mean, that's the theory of the software, where this is analytics and analysis. There's still a lot of application that we're going to kind of begin to understand cause and effect, cost benefit, all these different things that we're looking at with it. So 4.0 is the start of this journey. There will be a 4.1, 4.2. Anybody who buys 4.0 will get free upgrades to 4.1, 4.2, because as Andy just said, we are going to be crunching some of this data once with the software itself, and it will continue to evolve just like the PMC chart came about, maybe in a broader sense, but that is our vision, and we want to share that with everybody and do that, with everybody who participates in the WKO4 process.
I'm looking at the list of questions here, Tim, and there's one that I would like to take a stab at.
Great. Yeah, if you can read them directly, Andy, feel free. I just didn't want you to try to. I know doing both is hard, so I can shut up and just follow along if you want to answer.
Fortunately, I have 2 monitors now, which makes it easier, and also figured out how to expand that little tiny window. How satisfied are you with your model when it is fit to fiber types at both ends of the spectrum? Well, as I indicated in week 1, the data set against which I've been comparing the performance of all these models contains individuals all the way from world champion in ITT to world record holders and masters match sprinters. So we've got got quite a range already. Yet the model seems to work for all of them. So I am satisfied. You know, it's always better to have more and have more experience and see if you can break a model, see if you can find the limits of the domain of validity. But definitely tried to do so as much as possible, rather than just focusing on you know, only my data, nothing but a master's TT here. Um, let's see. Are there any questions in here that you have not answered that?
Could you answer Marcus's question? How well does the model predict FTP for a rider? See that one? It's about 5 down, 6 down.
6 down from the top.
Yeah, I can actually ask it to you. How well does the model predict FTP for a rider correlate with the actual FTP or the 95% of 20 minutes that we've been using?
Well, you know, I don't really know. I was going to go back to that, but they're interested in comparing not the model-derived FTP to what somebody does during a TT. They want to compare model-derived FTP to the 95% of 20-minute power. My answer would be is I don't know. I haven't looked at the data that way. It's going to be really close because there isn't a lot of variation between individuals at 20 minutes. By that point, your FRC contribution is starting to diminish quite a bit. And in fact, I've put up some plots where I've looked at, average power as a percentage of FTP. And once you get beyond about 2 minutes, the standard deviations are all quite small and quite comparable. But I could look at that and try and get an answer for that, maybe for next week if there's interest. The other thing to keep in mind, though, is that 95% of your 20-minute best is not Hunter's test. Hunter's test is to do the 5-minute blowout effort ahead of time, which is going to sort of take the edge off of your FRC and reduce the power that you're going to be able to produce for 20 minutes. So you might be expected to be more like 93% of your very best 20-minute power. But I can take a look at that. Again, the model-derived FTP here. I don't expect it's going to give people a tool to hone in on an accurate estimate of somebody's FTP, especially if they haven't done any formal testing or they really don't have a good feel for it. You see many new power meter users, especially triathletes, posting, what's my FTP? I thought it was this, I thought it was that, et cetera, et cetera. But on average, the model-derived FTP and what you would set based on, any of the 7 deadly sins are not going to be different.
So Andy, while you're looking, I'm going to pick one. I'm sold. Is pricing available? Yes, TrainingPeaks is going to be releasing information here very shortly. Release, as most of you know, is right around the corner and coming quickly. We're targeting December. The pricing is set. I don't know if it's available on TrainingPeaks. I don't know if I'm letting the cat out of the bag, but I will tell you that it is a $99 upgrade from WKO 3. You can choose your system at that time, your operating system, whether it's Mac or Windows. And you obviously can go forward in that operating system, whatever works for you. If you don't own it right now, I believe the new pricing is $149, and it really is going to be that clean and simple. What you can obviously see is Andy's showing some very tricky Mac screens on. We are functioning in Mac. We're deep in the Mac beta, and still continuing to. As a matter of fact, what Andy's showing is just one version back than what we're working on. So a lot of progress is being made there. So those announcements will be coming from TrainingPeaks. Look for emails shortly with more details, and we appreciate the interest. So Andy, any closing comments or questions you want to tackle?
I'm skimming quickly through the list of questions here to see if there was anything that would, everybody would be happy with. Yes, very much here. One question, we'll make this the last one because it's important. Does the model predict FTP well if some of the best power numbers are, for example, 50 seconds, 18 minutes, or 52 minutes, and not classic values, quote, like 1 minute, 5 minute, 20 minute, 60 minute? Yeah, the whole idea here is to leverage this huge amount of data, relatively speaking at least, that we have available to us. We've got all of these measurements of your presumably best effort at a wide range of durations. Why not take advantage of all of that information by coming up with a way of doing so from mathematical modeling? And in fact, you could, if you wanted, you could test the model by, let's say, eliminate all the odd durations, eliminate all the even durations. Well, you should get the same result, right? Because whether you set a personal best an odd duration in terms of seconds or an even duration in terms of seconds should be entirely random. And in fact, you can kind of look at the entire power duration curve and realize that you don't need all of those data points to define the shape of it. In fact, that leads back to people who are saying, well, I can just look at the shape of the curve without fitting a line to it. What's the advantage of fitting a line? So there's the opposite end of the spectrum too. If you were really into this, there is the Ikeki information criterion that you could view the model as a vast set of models that differ only in terms of which data points they utilize. And you could eliminate duration by duration using the AIC, and there's also the BIC, Bayesian information criterion, and decide that, well, the most information content is at 2 seconds, 12 seconds, 28 seconds, etc. But we have all of this data. It doesn't cost us anything to collect it, so we might as well use it. So it's different than modeling cases in the literature where scientific studies, physiological studies where you have to draw blood samples in a tracer study at specific time points and analyze them all. So a huge amount of labor and cost, in which case it's helpful to be able to focus on the subset that has the most information content because it saves you time and money. In this case, there is no cost of using all the data, so we just use all the data.
Excellent. Question about device agent. Everything you guys is being updated. I know TrainingPeaks is doing, and we're all doing a lot of work. Device agent is being updated. Some of the questions, we are continuing to try to make that a more and more streamlined process. Will there be an easy way to import data from WKO3 and other sources? Yes. Kevin Williams, the developer, has made a very smooth process for importing data. It'll find data from any previous version. Make it very smooth for your update. Okay, I think that is a pretty good wrap. Andy, thanks for your patience and great question answering. Everybody else, thank you so much for your interest. We appreciate you being on. Please join us again next week. A final announcement is once December 10th, Hunter and Andy are in mid-December are doing a large rollout presentation together, and then Hunter will be doing a series of 3 to 4 webinars on how to coach with WKO4, so taking the application and other stuff. So the team will be out there with a constant stream of education for everybody. So just know I'm going to work. TrainingPeaks and Hunter and I are working together tomorrow to put up some information about those dates and what that will be. So also know that there's more coming. Thanks, everybody. Have a great night.
Thank you, and good night.